What if I told you that humanity achieved one of its greatest technological miracles over 50 years ago, and today we can't repeat it the same way? It sounds impossible, almost absurd, but it's true, and it reveals something deeply uncomfortable about how progress actually works. In 1969, the United States successfully landed humans on the moon. Not only that, they brought them back safely and repeated this achievement 5 more times within just 3 years. 12,502 walked on the lunar surface between 1969 and 1972. This was done using computers far less powerful than the smartphone in your pocket, relying on slide rules, manual calculations, and primitive digital systems that now seem almost laughable. And yet today, with vastly superior computing power, advanced materials, and decades of additional scientific knowledge, we cannot simply repeat that exact same approach. Not because we don't want to, not because our priorities have completely shifted, but because, in a very real sense, we've lost the ability to do it the way it was originally done. This doesn't mean modern space agencies can't design new lunar missions. Programs like NASA's Artemis are actively working toward that goal. But here's the key point. We cannot recreate the Apollo program itself. We cannot rebuild the Saturn V rocket exactly as it was. We cannot reproduce the same systems, processes, and methods that once worked so flawlessly. This phenomenon is known as the loss of capability, or more broadly, the loss of knowledge. And it's not unique to space exploration. Throughout history, entire civilizations have lost technologies they once mastered. The Romans built aqueducts, roads, and concrete structures that medieval Europe struggled to replicate for centuries. The knowledge disappeared when the institutions that supported it collapsed. Medieval cathedrals relied on construction techniques passed through guilds, and when those systems faded, the methods were lost. Even the famous Damascus steel, once known for its strength and sharpness, cannot be perfectly recreated today. And now, in our own time, we've experienced something similar with the Apollo program. It's not that the technology is beyond us. It's that the ecosystem that made it possible no longer exists. The infrastructure, the supply chains, the trained workforce, the testing facilities, all of it has either disappeared, evolved, or been replaced. The knowledge didn't vanish overnight, but it slowly faded as systems were dismantled and priorities changed. To understand this more clearly, we need to look at the most powerful machine ever successfully flown, the Saturn V rocket. Standing 110 meters tall and weighing around 3,000 tons when fully fueled, the Saturn V could carry 140 tons into low Earth orbit or send 48 tons toward the moon. It was a masterpiece of engineering, and perhaps even more impressive, it worked flawlessly. 13 launches, 0 failures. But today, we cannot build it again. The production lines were shut down in the early 1970s. The specialized tools were discarded or sold. Facilities were repurposed or destroyed. Thousands of engineers and technicians moved on or retired. And with them, a huge amount of detailed, practical knowledge disappeared. You might think, but we still have the blueprints. And yes, we do. Technical drawings, specifications, documentation, they all exist. But here's the problem. Blueprints alone are not enough, because the most critical knowledge was never written down. That missing piece, the unwritten expertise, is what engineers call tacit knowledge. It lives in experience, not documents. It's the kind of understanding you gain only by solving thousands of small problems over time. And that's exactly what made the Saturn V possible. The blueprints don't tell you how workers managed to weld massive fuel tanks without causing microscopic fractures that could lead to catastrophic failure. They don't explain how teams tested and verified thousands of individual components under extreme conditions. They don't capture how contractors coordinated across different systems or how unexpected problems were solved in real time during production. Even if we had perfect documentation, we would still face another major challenge. The world that built the Saturn V no longer exists. Many of the materials used in the original design are no longer available. Suppliers that once manufactured highly specialized components have disappeared. Some went out of business decades ago, while others shifted to entirely different industries. Certain raw materials came from mines that are now closed. Manufacturing processes that were standard in the 1960s have become obsolete, and the machines used back then have either been scrapped or replaced. So even with all the original plans, we wouldn't actually be rebuilding the Saturn V. We would be forced to redesign it using modern equivalents, test everything again, and essentially create a new rocket that only resembles the original in capability. And that raises an important question. If rebuilding it costs nearly the same as designing something new, why go backward at all? That's exactly why NASA chose a different path. Instead of recreating the Saturn V, they developed the Space Launch System, or SLS, a completely modern rocket designed to match or exceed its capabilities using current technology. So when people say we can't build the Saturn V anymore, they're not exaggerating. It's literally true, not because we're less advanced, but because we've moved on. And that reveals something important about technological progress. It's not a straight line where every capability is preserved and improved over time. Instead, it behaves more like a branching tree. When we choose one path, we often abandon others. And the branches we stop maintaining eventually wither away. That's exactly what happened after Apollo. Once the moon missions ended, there was no longer a need for the Saturn V. The focus shifted toward the space shuttle, a reusable system that promised to make space travel more affordable and flexible. But that promise didn't fully materialize. The shuttle turned out to be expensive, limited in capacity, and tragically claimed the lives of 14 astronauts in two major disasters. By the time those realities became clear, it was already too late. The infrastructure behind the Saturn V had vanished, and the rocket wasn't the only thing we lost. The spacecraft that carried astronauts, the command module, the service module, and the lunar module also represent capabilities that are incredibly difficult to recreate today. The command module was a compact yet highly advanced system that supported 3 astronauts for up to 2 weeks. It handled navigation, communication, and life support, and it could survive re-entry at speeds of 11 kilometers per second, enduring temperatures of up to 5,000 degrees. Then, there was the lunar module, one of the most daring designs ever built. It separated from the command module in lunar orbit, carried 2 astronauts to the surface, functioned as their home for days, and then launched them back into orbit using a single engine that had to work perfectly on the first attempt. There was no margin for error. And just like the Saturn V, these spacecraft were built using techniques, materials, and expertise that no longer exist in their original form. And this is where the story becomes even more complex. Because what truly made Apollo possible wasn't just hardware. It was the environment that surrounded it, a unique combination of urgency, resources, and political will that no longer exists in the same way. The Apollo missions took place during the Cold War, at a time when the United States was locked in a fierce competition with the Soviet Union. Landing on the moon wasn't just a scientific goal, it was a statement of dominance, a demonstration of technological superiority on a global stage. And because of that, the level of commitment was extraordinary. At its peak in the mid-1960s, NASA's budget accounted for more than 4% of the entire federal budget. Adjusted for today, that's roughly $50 billion per year. And a huge portion of that funding was directed straight into the Apollo program. More than 400,000 people worked on Apollo, directly or indirectly. Engineers, technicians, scientists, manufacturers, an entire ecosystem focused on a single, clearly defined objective: land a human on the moon before the decade ended. That clarity made a massive difference. There was no confusion about priorities, no shifting goals, no long debates about whether the mission should continue. The objective was fixed, the deadline was firm, and the support from both the President and Congress was unwavering. This created an environment where problems were solved quickly and decisively. When technical challenges appeared, they were addressed immediately with whatever resources were needed. Budget constraints didn't block critical fixes. Bureaucracy didn't slow down decisions. And the culture itself encouraged bold thinking, rapid iteration, and a willingness to take risks. Take the F1 engines of the Saturn V, for example. During development, they suffered from severe combustion instability. Engines would literally tear themselves apart during testing. Solving this required countless experiments, redesigns, and adjustments, but the resources were there, and the problem was eventually overcome. Or consider the Apollo 1 disaster in 1967, where a cabin fire killed 3 astronauts during a ground test. It was a devastating tragedy. But instead of ending the program, it led to a complete redesign of the command module. The timeline was delayed by nearly 2 years, but the mission continued because the political will and funding were still in place. Now compare that to today. Modern NASA operates in a completely different environment. Its budget is around 0.5% of federal spending, less than 1/8 of what it was during Apollo. And that funding is spread across multiple programs, missions, and research areas. There's no single project receiving the same level of focus and resources that Apollo once had. At the same time, NASA has become far more cautious, and for good reason. The Challenger and Columbia disasters reshaped how the agency approaches risk. Today, every system is tested extensively, every decision is carefully reviewed, and safety is prioritized at every level. That's necessary when human lives are involved, but it also slows everything down and increases costs significantly. On top of that, there's another challenge: political instability. Unlike Apollo, modern space programs are heavily influenced by changing administrations. Every few years, priorities shift. Programs are started, canceled, redesigned, and restarted. Long-term planning becomes extremely difficult when you don't know if your project will survive the next election cycle. The Constellation program is a perfect example. It was launched in 2005 with the goal of returning humans to the moon, but after billions of dollars and years of development, it was canceled in 2010. Then came the Artemis program in 2017, with a similar goal but a completely different approach. And even now, there's no absolute guarantee that Artemis will continue long enough to fully succeed. This constant cycle doesn't just waste money, it breaks momentum. Engineers spend years working on systems that never reach completion. Teams are disbanded, knowledge is lost, and contractors become hesitant to invest in capabilities that might not be needed in a few years. The result is a slower progress, higher costs, and a growing gap between ambition and execution. And that's where the deeper problem becomes clear, because it's not just about technology anymore, it's about whether we can sustain the systems needed to support it. And once you start looking at it that way, the problem becomes much bigger than rockets or spacecraft. It becomes a question of stability. Because even the most advanced technology cannot succeed in an environment that constantly resets itself. One of the clearest examples of this issue is the supply chain that once supported the Apollo program. Building the Saturn V and the Apollo spacecraft wasn't the work of a single organization. It required thousands of components produced by hundreds of specialized suppliers. Each of those components had to meet strict standards, and coordinating all of it required years of refinement. Many of those suppliers were small, highly specialized companies. They focused on producing very specific parts, components that had no use outside the space program. And while Apollo was active, these companies thrived. They developed expertise, trained workers, and optimized their production processes. But when Apollo ended, the demand disappeared almost overnight. Without contracts to sustain them, many of these companies shut down. Others moved into different industries. The equipment they used was sold off or scrapped. Skilled workers retired or found new jobs. And with that, a huge portion of the industrial knowledge that supported lunar missions simply vanished. Rebuilding that kind of supply chain today isn't impossible, but it's extremely difficult. It would require identifying new suppliers, developing new manufacturing processes, and qualifying every single component again. That process alone would take years and cost enormous amounts of money. And there's another complication. Modern manufacturing works very differently compared to the 1960s. Back then, production systems were often more self-contained. Large programs like Apollo built dedicated supply chains designed specifically for their needs. Today, manufacturing is far more global and efficiency-driven. Companies rely on just-in-time supply chains where parts arrive exactly when needed, minimizing storage and reducing costs. While this approach is economically efficient, it also introduces new vulnerabilities. Supply chains are more fragile, more dependent on global conditions, and less suited for highly specialized one-off projects like Apollo. So even if we tried to recreate the same system, we'd be doing it in a world that operates very differently. And this brings us to an important realization. The challenge of returning to the moon isn't just about building better technology, it's about rebuilding entire systems that no longer exist. Because space exploration isn't a steady, uninterrupted climb upward. It's more like a series of peaks and valleys. Progress happens, then slows, then sometimes even reverses. And when capabilities aren't maintained, they fade away. The Apollo program is just one example of a much larger pattern. Throughout history, societies have lost skills, technologies, and knowledge during periods of transition. Sometimes it's due to economic shifts, sometimes political instability, sometimes simply because priorities change. And when that happens, even the most advanced achievements can become difficult or impossible to reproduce. So the real question isn't just how we get back to the moon, it's how we avoid losing that ability again. To answer that, we need to look at what has worked in more recent history, because not all space programs have followed the same path as Apollo. Some have managed to maintain continuity, preserve knowledge, and build long-term stability. A perfect example of this is the International Space Station. Unlike Apollo, which was designed as a short-term mission with a clear end, the International Space Station was built for continuity. It wasn't about reaching a single milestone, it was about maintaining a Postayana human presence in space over decades. And that difference changes everything. The station has been continuously inhabited for more than 20 years. Through political changes, budget pressures, and global crises, it has remained operational. Not because it's simple, but because it was structured to survive. One of the key reasons for that stability is international collaboration. The station is not owned by a single country. It's a joint effort involving the United States, Russia, Europe, Japan, Canada, and others. Each partner contributes modules, resources, and expertise. And because so many nations are involved, Canceling the program becomes much more difficult. Ending it wouldn't just stop a project, it would damage international relationships and credibility. That creates a powerful incentive to keep it going. At the same time, the station has allowed space agencies to maintain critical knowledge. Engineers, scientists, and astronauts continue to gain experience working in space. Systems are continuously tested, improved, and refined. Instead of losing capability, it's being sustained and evolved over time. It's not perfect. The station has limitations, but it demonstrates something important. Long-term presence in space is possible if programs are designed for sustainability rather than short-term success. And that lesson is now shaping the next phase of lunar exploration. Because unlike Apollo, the goal today isn't just to land on the moon again, it's to stay there. And that's exactly where the Artemis program comes in. And this is where the approach to space exploration begins to change in a fundamental way. Because the Artemis program isn't trying to repeat Apollo, it's trying to move beyond it. The goal is no longer just to land astronauts on the moon and return them safely. This time, the objective is to build something that lasts, a long-term presence, a system that can be expanded, reused, and sustained over time instead of being shut down after a few missions. But achieving that vision is far more complex than what Apollo attempted. Instead of relying on a single rocket and a tightly integrated spacecraft, Artemis depends on multiple systems working together. At the center of it is the Space Launch System, or SLS, designed to carry heavy payloads beyond Earth's orbit. Then there's the Orion capsule, built to transport astronauts safely through deep space. And beyond that, there's the Lunar Gateway, a planned space station that will orbit the moon and serve as a staging point for future missions. And that's only part of the picture. Private companies like SpaceX and Blue Origin are expected to play a major role, developing and operating the landers that will take astronauts from lunar orbit down to the surface. This introduces a new layer of collaboration, one that blends government programs with commercial innovation. On paper, it's a powerful idea, a flexible, distributed system that can evolve over time. But in reality, it also introduces new challenges. Each component has its own timeline, its own budget, and its own technical hurdles. Coordinating all of them requires a level of organization that is far more complicated than Apollo's relatively direct approach. And that complexity has already started to show. The SLS alone has cost more than $20 billion to develop, yet it has completed only a single uncrewed test flight as of 2022. The Orion capsule has also exceeded $20 billion in development costs, with its first crewed mission delayed until at least 2026, nearly 2 decades after the project began. This highlights a difficult reality. Even with better technology, more advanced tools, and decades of experience, modern space programs are often slower and more expensive than their predecessors. Part of that is due to stricter safety standards, which are absolutely necessary when human lives are involved. But part of it also comes from the increased complexity of modern systems and the fragmented nature of institutional support. In a way, we're paying the price for lost continuity. Because rebuilding the capability to go to the moon isn't just about designing new hardware. It's about recreating the workforce, the infrastructure, and the supply chains that once existed, and doing it in a world that has changed significantly. And that raises an uncomfortable question. Was it worth letting that capability disappear in the first place? Because now, decades later, we are spending enormous amounts of money to rebuild something we once had. If lunar missions had continued, even at a smaller scale, much of that knowledge and infrastructure could have been preserved. The cost of returning today might have been far lower. Instead, we are effectively relearning what was already known. And this leads to one of the most important lessons in the entire story. Technological progress is not automatic. It doesn't simply move forward on its own. It requires maintenance. It requires continuity. And when that continuity is broken, progress can stall or even reverse. The decision to end the Apollo program may have made sense in the short term. Priorities shifted. Budgets changed. The immediate goal had been achieved, but in the long term, that decision came with a cost measured not just in money, but in lost capability. So if we want a different outcome in the future, we have to think differently. We have to decide which capabilities are worth preserving, even when they're not immediately needed. We have to build systems that can survive beyond political cycles, and we have to recognize that some achievements are too important to let fade away. Because if we don't, we risk repeating the same cycle again. And that brings us to the final piece of the story, what all of this really means for the future of humanity in space. Because the story of Apollo isn't just about rockets, or the moon, or even NASA. It's about something much deeper, how human ambition interacts with its own limitations. On one hand, Apollo stands as one of the greatest achievements in human history. It proved that, when fully committed, humanity can solve incredibly complex problems and reach goals that once seemed impossible. It showed what can happen when resources, talent, and political will are perfectly aligned. But on the other hand, it also revealed how fragile that success can be, because the moment those conditions changed, the system that made Apollo possible began to disappear. The infrastructure was dismantled, the workforce moved on, the knowledge slowly faded, and within a few years, one of humanity's most advanced capabilities was no longer within reach in its original form. That's the paradox. We were capable of reaching the moon, but not capable of sustaining that capability. And that's the real challenge moving forward. If the future of space exploration is going to be more than a series of short-lived achievements, it needs to be built on something stronger than temporary alignment. It needs stability. It needs long-term thinking. And most importantly, it needs continuity. That's why modern programs are shifting toward collaboration. International partnerships, commercial involvement, and incremental development are all attempts to create systems that can endure. The International Space Station showed that this kind of model can work. Artemis is trying to extend that idea beyond Earth orbit. But success is not guaranteed, because the same risks still exist: political changes, budget constraints, shifting priorities, and unless those challenges are addressed, even the most ambitious programs can struggle to survive. So the lesson here is not just technical, it's strategic. If we want a permanent presence on the moon, or eventually on Mars, we need to design programs that can outlast individual governments, economic cycles, and short-term goals. We need to treat space exploration as a long-term commitment, not a temporary project. And that requires a shift in mindset. It means accepting that progress in space will take generations, that the benefits may not be immediate, and that the true value lies not just in reaching a destination, but in maintaining the ability to return and to keep going further. Because without that continuity, every breakthrough risks becoming temporary. Every achievement risks being forgotten, and every step forward risks being followed by a step back. The story of Apollo is both an inspiration and a warning. It shows us what we can achieve at our best, but also what we can lose when we fail to sustain it. So as we look toward the future, toward the moon, Mars, and beyond, the real question isn't just whether we can get there again, it's whether we can stay. Because this time, success won't be defined by a single landing. It will be defined by whether humanity can turn exploration into something lasting, something continuous, something that doesn't disappear the moment we look away.